Okay, everyone. So, a couple of things before we start, right? I just want to recap a few things. So first, so last week, meaning this weekend, I finished the 2 videos, and I think one was for the October 24th and 26th. So I looked at the total time; it comes to about the total class time. So we will not really cut corners there. So the 24th class, as you saw, I continued with the football helmet analysis. I walked through the other aspects we had not covered, right? Like the padding, and then we went into the assembly and the face mask, chin strap, the rationale for the materials and paintability. And so I'd invite you to kind of look at that analysis and think of that approach for any product that you look at. Go into as much critical analysis as you can, both qualitative and quantitative. So that really help you define bottlenecks, like simple things like where to drill the holes for attachments. You normally would not think of it unless you really pay attention to that aspect of it. So along with that, I gave you 2 more things to think about. One was a tennis racket and one was a ski, just as 2 other case studies to I didn't go into as much detail in analyzing those, but you can see tennis rackets have come a long way, right? From aluminum to even titanium, then graphite, and now of course graphite and titanium are competing, but it's an application where you want flexibility and rigidity at the same time. It's counter to each other, but it's very cleverly, as you can see, designed from the shape, cross-section, and the entire ways of suppressing vibrations, if not you get the tennis elbow injury and everything, right? So that's minimized quite a bit over the years. The third application we saw, ski, is a very complex structure. We saw that it has 7-8 layers. Each layer does very unique things, and depending on the price point, the core can go from highly engineered core to a very standard balsa wood core. Right? So there could be the difference in price points from that standpoint. So the whole purpose of that exercise was holistic thinking when it comes to the product. Then the last class, 26th class, I tried to cover the process universe part of it, and there I know I went a little fast, but what I've done is given you a range of processes that apply to polymers and composites. More I focused on that in that video, I guess, because we have talked about metals earlier in the forging, rolling, and all of that, casting. So as you go into Granta and so on, now all the processes that show up, it will be a lot more meaningful, hopefully, that now that you have a sort of an idea about, and some of you took the class last semester, we went into a lot more detail there. So today I will get into tooling, and there also we will tie it back to the processes. So this way, I think we have not lost the last week's class. Second thing is I have finally graded the most of the stuff, except for sheet metal. I have graded everything now, so it was done. I have done a couple of things. I have your mini projects here. So the mini projects, I will just mention that everybody really did a good job on it. I think there are 3 or 4 pieces of work which were really outstanding and way beyond even what the expected level of the requirement was. And what I will do is I'll mask the names and post those as examples of what best works look like. And it's not for putting anybody down or up or anything, it's just to give you a feel for what is really required in the real engineered product, for example. So I graded this, I think, out of 100, and I didn't look in detail about your calculations and so on. I looked at how you approach this thing and saw that many of you followed the examples given, and I think it was really well done overall. The third thing was the test 1. So there what I did is you have a CAD portion and you have a theory portion, right? I mean, CAD portion, as you can imagine, it's all over the place based on the files I have received, and I'm trying my best to open as many and look at all the details. So I can't say that's a perfect, what do you call as process by any means. I'm doing it as best as I can. So what I've done on the theory part is converted to PDF if you didn't put it as PDF, and I've added comments to that as I could, and then I posted those back to Canvas so that you can open and at least look at the grade. And that file on the top, I gave you a grade for the theory part out of 100 and for the CAD part out of 100. And the CAD grade is based on my impressions of, I can tell you I've not gone into each dimension and checked this, it's not impossible to do. But and there again I will post some good work. Some of you did some outstanding job of putting the animation videos, so there I will post examples of what a good theory looked like and what a good CAD looked like. So that way you have a feel for this. On this I would like to mention, when it came to the theory part, I looked at it in more detail. One thing is, I think I probably didn't stress this enough, this is a take-home exam, right? So the idea of a take-home exam is not to put 3 bullets and say take it or leave it, right? You need to spend enough time to critically analyze the thing and there's a lot of literature out there. It's a matter of going and finding that information. So also then try to find out as much quantitative information as you can, because just giving qualitative statements like this is big, that's small, or this is great and that's not too great doesn't tell much. You have to add facts, figures, have a basis for reporting this paper, this is the data that came out of that. In other words, when you think of the problem, think in the industry, if you were asked to compare 2 steels, what all would you do, right? You would have to go out and look at as much as you can find about it, and then come up with a reasonable rationale for why one would work, say for stamping, why one would not work. It's not just based on judgment or qualitative statements. You want to be based on facts and figures. So that's why I tried to give you that feedback. And some works again were outstanding here. Some could use some more work kind of thing. But I think overall, and calculations in problems like the R by T and the punch force, show the steps of the calculation. Just if you plug it into MATLAB and put an output, I wouldn't know if it's how you did it, right? So you need to have a step-by-step of how you approach it. So handwritten stuff was fine. If you scanned it, I don't really need it to be typed or anything. And then on the forming limit diagram, the same thing. The B pillar case study, that was just a B pillar. But if you look out there, there is a very vast body of literature on sheet metal, Taylor-Will blanks, forms. So my idea was to look at that component, how much literature did you go out and hunt to see how you can analyze that and show where the strains would be, what the critical strain. Not just tell me what a Taylor-Will blank looked like and this is what it does, because that we have covered in class, right? So you should go beyond that course. So just some feedback like that. But again, everybody did fine there. I think the class average on this test was a 182 out of 200, which is not bad at all, I think. And I'm giving you qualitative feedback here, obviously, not every single point here and 2 points there. It's not a statics or dynamics class. Right? So this I have already done. The 4th one that I owe you was the motor blower assembly. So these I have posted the grade to the website, and again I can sit with you if you want to know specifically how I looked at it. There I did the same like I did with the CAD here. I opened the files as best as I could, look from the assembly, and then I worked back into the parts to see if there was any basic issues. But again, remember the purpose of this assignment was to get you into that habit of going from concept, start actually working parts in the CAD software, trying to put it into assemblies. I think it will help you down the road, right? When you look at developing products and so on. The more you have a confidence in doing it yourself, the less you're relying on your design engineers, because you have at least you can communicate a lot better with that body of engineers in your firm and so on. Let's see. And as far as the handouts, my handouts may not be up to date to the content yet. I'll just check where I'm missing and update those as well. I've given you also, I forgot that, a test 2, and like I said in the class last time, the test 2, the class before that, will be given in 2 parts. One part I gave out was the one tied to doing some problem solving mechanics, basic mechanics, and then one was there are at least 3 case studies where you are going to use the CES pack and then do the exercise what we did in the class from translation through the whole. Yes, sir.
Do we need to include the process stuff on the CS Granta?
So for those assignments, not necessarily. We'll do the part 2 part where I may give a specific case to get more into the process side of it. So this is more geared towards materials selection. Again, I'm sorry for the delay in some of this graded work, and one thing I have to grade is out of 50 points the sheet metal part, but otherwise we are caught up. Any questions, or am I missing anything here? Everybody could see the videos, fine, okay. That's.
It looks like for the 24th, your last video kind of like cut off. You were in the middle of saying something at the very end. There's like a 6-minute video. You were in the middle of saying something, and the video just ended. And I was like, well, hopefully.
At the last part, or was it?
Like the October 24th, you uploaded 3 videos. There's like a 20-minute, 26-minute.
The last one is only a 6-minute video.
Yeah. It like cut off when you were mid-sentence. So I don't know.
Yeah, it's just because my wife was telling something and I had to pay attention to her. That's why I cut off. So no, I can't remember there, but I know there was a reason for this. So she was already mad. What's going on? I mean, all afternoon they said, wait a minute, we have to do this. I can't think of any other reasons right now.
Sheer terror.
Sheer terror. I was telling Stephen the way I've done this, and if you guys know a better way, let me know. But I have the iPad is there's an app called Whittle in there. So what Zoom does is when you say share screen, so I invite myself to Zoom, right? Like there's nobody on the other side. So it's a weird feeling. You invite yourself, you turn on the video, and then you say share screen. It'll ask you which screen you want to share. So if you say I want to share the iPad, then I turn on that app in iPad. That becomes a whiteboard then. So whatever I write there is what you see. And the recording, you can record it. It seemed to work okay, but if you all have suggestions, please let me know. So yeah, now we are, today I'll digress now. I think we have spent good amount of time on the Granta in terms of materials and process. I'll come back to it for finishing up shapes and hybrid and cost. There are 3 things, but I think I can cover that maybe in 1 or 2 classes now that you know the structure of that software. Today what I want to do is go into another aspect that is very important in product development, and that refers to tooling. And we kind of touched upon this as we have talked through, but it's really a very critical piece of the product development, right? Tooling. Now, both from the standpoint of concept stage, that is from the standpoint of prototyping stage, and then from the manufacturing, right? So there are very different things here. So when you talk of prototyping, you're talking what? In terms of generally low volume parts, right? You're just trying to prove out a concept. So basically you're doing concept to creation, basically. And therefore there's a lot of consideration given here for what? The economics, because you want to engage the customer, but you don't want to basically steal the bank, or like you say, break the bank for the customer, because they would be very hesitant to go forward if they see that a lot of money is sunk into tooling before they even know if the product is going to work or not. So there is a big challenge here about how do you go about it, right? But at the same time, every customer will want to touch, feel, and experience and so on, and they want to know exactly how will my product look, how will it feel to touch, how will it appear, what are the aesthetics of the product, what is the functional, does it do the functional requirements and everything like that. So there is a lot of thing in demand the customer has, but at the same time they don't want to pay too much money to do that, right? So it's a classic problem where you are telling them, listen, these are the, and I go through this actually on a weekly basis. I have some customers, meaning sponsors, who I want this done, I want this, by the way, it should do this, that, but, and how much great can we, and by the way, can you cover it through your cost, because you are a university, you should be able to, they think that if you are a university or a lab, it should be free work. I mean, why should we even have to pay for it? So that's the mindset they come with. But when they hear the pricing, then sometimes they don't return your calls after that, or so there's all kinds of concerns with cost go on from the prototyping standpoint. But as a designer, you should know this can be a big bottleneck. So some things we'll talk about today relate to how do you work despite the challenges of cost. How do you still get the performance or the to move forward, actually. And this is where, for example, additive tooling or additive manufacturing has become very important. Of course, CNC knowledge, that if you have as much CNC knowledge and capability in-house, that's a very big plus. Also materials used in tooling. As you can see that just from going with lower cost materials, you can go with lower manufacturing processes and bring the cost down overall that way. So there are many ways to approach this aspect of it. And you can be, of course, very creative sometimes in the tooling, because the customer does not care what is used to make the prototype. They are just worried about the actual prototype itself. But you could be very creative in terms of putting together the tool just to overcome the bottleneck. When they are convinced, they are very much, at the end of the day, your goal is to go from this left side to the right side, right? They should commit to the high volume tooling. And when I say tool, I hope everybody understands, I mean the mold or what is used to shape the part. So that is what I'm referring to. So you want them to go from low to high volume manufacturing, of course. Why high volume tooling? Because this is true production tools. So sometimes what you have done on the left side does not entirely translate to the right side. You have to look at it from a different mentality or a mindset. So you have to be very much familiar with what are the volumes you're working with, what is the cost limiting cost, how much is the customer willing to pay, what is the source of the tooling, is it a recurring expense or is it like a non-recurring expense, for example, and we'll talk about this in terms of manufacturing process. A tool cost is generally considered as non-recurring. It's a one-time investment, which is a chunk of the money used to buy the tool or produce the tool, but later that is not accounted for in the costing or accounting standard. It's a one-time investment. So sometimes the source for that could be very different. Who is paying for it could be very different from the manufacturing costs, which accounts for materials, your electrical bills and the water bills and plumbing, and those are all recurring expenses, right? So you can separate this from, and that also has to be known. The other thing you need to know is your cost including amortization of the part, and I think I mentioned this a few classes ago. Amortization comes into play when you do high volume manufacturing, because you build in the cost of the tool into the cost of the part, right? So if your tool costs $1,000 and you make your part costs has to be at least $1,000 plus whatever else it is. Which means if you make one part, the $1,000 from that is the tool cost. If you make two parts, $500 of the tool goes into there, right? If you make 10 parts, $100, like that. So the more parts you make, the cost of the tooling in that starts shrinking and shrinking. So if you make 50,000 parts for a tool that costs, let's say, 40, 50K to make, the cost of the tool becomes like $1 per part. So it really helps you, volumes help you in making the tools almost inconsequential. And that's the philosophy most of the high volume manufacturing people take. But if you're making only 10 parts over the year, then you need to change your tooling strategy, because you've got to go for low cost tooling options. Otherwise you can never make any profit from that, right? You're paying and the customer has a certain threshold that they're willing to pay. So this becomes a bottleneck based on volume actually. So this is some of the economics of tooling, and like I said, tooling is I really have a lot of respect for tool makers. It's one of the most complicated things in the field of manufacturing, and the art of tooling is dying, right? I mean, there's how many tool and die makers do you have left? All the young people are going to IT, or they're going to additive or some fancy thing, nano, but nobody wants to go into a tool and die and learn the trade skills. So
Yeah, I think we've lost something like 80% of the die makers in the U.S. since 1995.
that's true, and they're all outsourced, mostly Taiwan, China, India, right? Most of the tooling is head that way now. And the US, of course, still there's a very wealth of tooling knowledge in the Midwest. You go to Wisconsin, Ohio, Michigan, that areas, you'll see most of the US tool manufacturer concentration is in those states. And wonderful quality work, but just the economics are such they're not able to sustain based on the price competition from what China-made tools could be 30-40% cheaper for the same everything. And then, so obviously there is going to be, and when you're investing 100K in a tool, and if you can save 30-40% cost, you're going to look at overseas as an option. And that's the reality of it. So companies like, and I may have said this earlier, sometimes I repeat myself, the companies like Quick Parts and Prototypes, they're going to ask you, when you have a part which is of the size of this seat, what's your lead time? Okay, my lead time is 6 weeks. Okay, then it will be in the US, but your cost is going to be 30 times more. If you are willing to wait 8 weeks or 12 weeks, they will say we'll give you 30% less cost, but then it will be an overseas made tool, and you. So sometimes time becomes the decision factor, right? If you are willing to wait, then you can really make it cheap and do it that way. So there is a lot that goes into this decision. So these are really just a partial list of options. So you can make tooling from a whole range of materials. Of course, some very robust and some of the best material is wood, of course. And it's very common to have mahogany, maple, or other hardwoods used to produce. I think in the video last time when I showed you the ski things, I had a ranking of woods there, soft to hard. So here we are talking about the right scale of that hardwoods. And usually when you do tooling with woods, you normally don't use a monolithic wood, right? What you do is you actually laminate the wood like glue lam like this. So you bond it together, right? And then you cut your forms with that bonded wood. So this is usually referred to as glue lam because it's glued laminated wood actually. So if you look at it, you'll see striations of dark and soft and dark and soft. And the reason for doing that is you average out any anomalies because it's a plant after all, right? So you're getting cell to cell variations and so on. So to average all that out, when you do this kind of laminated wood, different hardwoods, then the wood becomes very, in a equivalent, in an average fashion, it has very similar attributes, compression strength and everything. And then you can get very uniform quality product. You can still get, you'll be amazed by how many parts you can get out of a wood tool. Wood is very commonly used, for example, in thermoforming operations. For the most part, you just want to get a shape of that. You can also use it as a base for a lot of the FRP processes, like fiber reinforced processes to produce, where there's not that much of compression on the wood. Where it does not work too well is in a closed cavity tool, when you want to bring two parts together, male and female, and apply excess of 100 psi, then the wood cells can start micro cracking, which makes it a little bit challenging. But it's very much an approach. Then you have the second one called Ren board. Ren board is just a trade name. It's basically mostly like a polyurethane wood, right? It is it's a synthetic because it's made out of primarily polyurethane resin with some particles, or it could even be wood adds or gypsum, other things added to it. It has a certain nice quality about it, where it can be machined readily, and it can come in a range of hardnesses, so you can produce very high quality tooling with Ren board. So Ren board can be bought in sheets, different thicknesses from 1/2 inch to 8 inches thick sheets. And there also you can glue them, laminate them to build up larger structures if needed. But it's very much used by industry for doing, you can get very high compression strengths with this type of wood. So today is Halloween, of course. You'll see that a lot of artists are using silicone for producing masks and all your Halloween wear, right? And those are all flexible, mostly elastomeric. You can wear a mask and do all those things. So the artist community uses a lot of gypsum, plaster, silicone when they produce their tools, for example. So I've not jumped the gun, but I'll show you. I think I had this towards the end somewhere. And, because it is Halloween, I'll show you this first. So if you look at, this is what I mean, right? So silicone is a wonderful material that helps you produce a very range of complex shapes. And I don't have a mask on here, but typically most of your masks are made the same way, right? So here you have, if you have a certain product or an existing product even that you're trying to duplicate, you can actually take that and you can place it in a box in the center, essentially hold it in the center, and you can pour silicone through the entire structure and build up, like if this is your part here, let's say whatever, you build up a silicone dam around it on both sides basically, and then carefully when you cut the slice after it cures, you already get a male and a female to work with, like you get in this case, this is the part and these are the two halves that is drawn. You can see it is basically just shaved off with a hacksaw basically, right, after it's done. So now you can make infinite number of parts, not infinite meaning a lot of parts, just with a basic tool that is replicating a shape that you're already working with. So sometimes in early prototyping what you can do is, if you have a shape or a part or a product in mind, you can take that and start working some basic prototypes with that approach. Because you can at least get the customer to say, hey, this is not the exact final size, but this is the overall features that you're going to get in your part. And the part can be made with any material later, but the tooling, you can completely get tooling made. This may be less than $50, for example, right, to produce a tool, which otherwise if you take a machine block from aluminum, make this two halves, at least you're paying upwards of $2,000 to get that tool made. So there are clever ways of producing low-cost tooling, and in this case, the best way is to look at the examples on Smooth On, and some of you may have used this site But Smooth-On has a wonderful range of products that they demo step by step architectural infrastructure, products. I mean, you can athletics. You can go into any number of products and produce this one. But it's a website worth visiting.
I've got a friend that uses a 3D FDM type printer to print parts that then he cast molds.
You can do that, yes, exactly. You can cast molds that way too. I mean, there's a lot of low-cost ways of producing this.
Yeah, I just thought it was pretty cool to just to go from the 3D printed object and then be able to produce quite a number of duplicates.
Parts from that. So you first take a CAD, make a 3D.
Mm-hmm.
From that 3D, you reverse engineer, make your tooling, then produce that any number of parts from that, right? So there could be that one. This one now has gone into more crazy things, like here, has found that sculpting and theater. A lot of the theater guys work with this a lot actually. So you can actually, and this is alloying, right? Yeah, it is alloying, right? So you can see that they are making this, of course it's a non-toxic mixture, you don't want to apply it and then go to the doctor later, right? You want to make sure it is non-toxic, it's completely free. So you can make your exact shape, you can pull out that shape, and from that you can be producing parts from, for further work. Also you can pigment it red, etc. So you can make very complex arteries to show. A lot of the medical students, for example, could learn from these kind of dummies. So there's an industry out there which produces dummies of the intestine, liver, kidney, pancreas, and so on, made with this material because it has that soft touch feel to it. It feels like the human body in many ways. So now these things, virtually also you can think of it as haptic devices, like you have things you can put on your fingers, and when you touch that, if it's a model, you can actually feel the texture of the object. If it's a skin, it will feel like a skin. If it's a skull, it will feel like a skull, like that. So you can make it as real to your customer as possible with this approach. So this is a possibility, like I said, in low-cost tooling, to look at latex, silicone, elastomer-based tooling. Of course, if anyone has worked through all this, please share your experiences. I'm just giving you some thoughts.
Make sure to degas the silicone.
That's correct. Oh yes, it's a pain. Absolutely.
Also get bubbles, which
You want to say a little bit, Alex, about your work with this? Because I know you've done a bunch of.
I mean, I've done some prototyping molds with silicone and with urethanes, and it is basically how you outlined. You have to take into account where you're going to put the sprue so that you can actually cast in whatever material you're going to cast in. But my impression is that it's mostly the thermosets that you're working with.
Yep.
That you're not going to be using this for injection molding prototypes or things.
You don't want it to stick later because silicone can bond down to the other surfaces too. You can get that problem. In fact, I forgot to mention one thing there. A lot of the times when you do that two-part mold, what you're doing is you're actually creating grooves like this in that. So what happens is after the part is, you cut that open, this actually acts as interlock. So this has a hole and this has a nail like that. So later when you assemble it, it's like a mechanical interlock. So your mold doesn't move around when you're casting your parts later. So you can do a lot of tricks right at this stage so that the part becomes very stable later. And there's no variability from part to part actually.
Yeah.
There's a pressure pot.
Yeah. Yeah, no, that's what I've ended up using is pressure pots for that.
But you evacuate the mold, right?
Yeah.
So this is
Vacuum and pressure pot combination gets the best.
the best thing to, like I said, for this part, maybe I'll write in when I post this, is to visit that website for Smooth-On and spend a day on it, and you can learn everything about it. Of course, the sweet medium between everything is aluminum. So when you have to work with a robust process, you may have to do maybe few hundreds or even few thousands of parts. In that case, aluminum does do a good job of providing you that option. For one, aluminum conducts heat very readily. So most of the tooling you have to get heat into the charge or the material you're molding. and aluminum helps you do that, right? It actually provides for conduction of heat. There is, of course, limitation in terms of high compression pressures. Aluminum is ductile after all. As you can imagine, its stress behavior is like that, right? So you can see that with continuous use, you're starting to deform the tool. In all these assumptions here is the tool should be non-deforming, because if the tool deforms, you've lost the accuracy of your part as such. But aluminum wheel is used anywhere from few hundred parts to, it's not uncommon to do greater than 5,000 parts even. It all depends on how well you're taking care of the tool. Obviously it works very well for low pressure processes. The workhorse of tooling for production tooling is tool steel, and tool steel, as you know, basically has a high hardness, right? It has a high hardness. Typically, the hardness could be like 38 to 42 Rockwell hardness. So, on the hardness scale. So these are of course expensive. P20 and H13 are the industry names for these tools. And again, here I invite you to look up their properties. Even in Granta, if you look for unstructured information, you can get a lot of detail on this tooling. These are, P20 is more machinable than H13 in terms of the hardness. And a lot of the reason the tool cost for steel is high is because the cost of machining is high. To get the same amount of aluminum machine, you're going to require maybe 1.5 to twice as much time to get the tool to machine to that level. So that's why.
Yep. Going back to aluminum, what temperatures are you using? Would you use that with? I mean, aluminum has good heat transfer properties, but it also has like massive thermal expansion. Does that cause a problem?
It does, yes. Actually, that's a good point, right? So when you're doing aluminum tooling, typically the use temperature, if you're doing like pre-preg parts, for example, 350 to 400 F would be like your repeat use. Anything beyond that, it can handle transient cycles, but not more, because like you said, it will tend to expand a lot. The other thing is, if you're not too concerned about thickness tolerance you can get, but if there is some further post trimming going on, then you can accommodate for that expansion as well. You can also build it into the design of your part and account for some expansion from that. Like you do polymer, you'll see what is the shrinkage. If you're working with polypropylene, you have to account for 5-6% shrinkage, right? If you fill that with 20-30% glass, your shrinkage may down to 2-3%. So it's a function of your material and the tool that's used in there. Like aluminum in a pure polypropylene would be like extreme. Polypropylene wants to go crazy in expansions, and so does aluminum. So you have to account for that in the final geometry.
There's other tricks you can take to get your tooling costs down too. You can run stock frames. You can use, rather than have automated second reactions, you can do insert tooling, remove, do manual removal. You can modify the part design so that you assemble more parts than you would normally. There's other tricks you can play to get the cost down. Size of the tool.
Can you expand a little bit on the stock tooling for the benefit of the class?
Yeah, so I worked injection compression molding for about 10 years, and most of the big customers buy their own tools, so it'll be custom built, and you design the tool to optimize the cycle time, so you keep the piece price down on the parts. But for customers that don't want to do that, then sometimes you'd have stock frames, which is a frame that you built that's built to your standards, and then it's designed to take a wide range of tooling inserts from cavities and cores within certain footprints. So if you want a part and you don't want to pay for the whole tool, then I'll give you a cost break. You only pay for the inserts, and I give you a little bit of upcharge for hours on my frame that allows smaller companies to get products out there or to test them. And you see that used a lot in prototype and stock frames. Prototype shops and their stock in trade is typically they have a lot of different stock frames that they have, and then they just charge you for the insert plus a small profit.
So is that like the kind of thing that Proto Labs does?
Yeah, they maintain some stock frames. They'll do other stuff for you, and the prototype market's really branched out a lot with that manufacturing to where you can get pretty fair functionality out of a lot of the grades of plastics that you can run. It used to be that you would do a hard SLA, and then you'd make what was called an RTV mold out of a polyurethane, and you'd have lower pressure injection of a different polymer that's not your standard, but it gave you better, closer properties so the customer could feel it and play with it for a while before they broke it.
Yeah. Yeah, that's a good point. When we go to an injection, we work with our injection mold, he has what is called the mud units, MUD units, which are like your base frames, what Stephen is saying. So that way you don't build, if you're making a mold, you don't have to build the entire thing. You're just building a small insert which fits within that overall geometry. So if it is a part of say 10 inch by 10 inch by say 2 inches and the frame is 12 by 12 by 4, it can easily hold that insert. So that all the cost of building that frame is eliminated and you're just going for a small part of it. So
Okay, I don't know what happened to them, but there was a company about, I guess, 14 years ago now that was doing additive manufacture of the inserts out of it was basically a polymer bronze combination. They print up the tool, bake off the resin, and then vacuum infiltrate material so that they could turn around a basic set of cores and cavities in a single night.
okay.
They were at the NPE at McCormick in Chicago. They were doing a demo to where you would sit down and CAD up a part one day, and the next morning you'd come in and they'd have their stock tool running.
Ready, I see. I'm sure a lot of those are still there, and that's where I think like overnight quick parts and prototype work in 2 days, they can get you your part, right? So I'm sure that technology has proliferated. It's no longer one company, it is more segmented, I believe. And it's amazing, right, how accurate those things still work out. Yeah, but this business of inserts is very much used a lot. In fact, we use it in our own work quite a bit. So, and I think Jared, you can watch to that, right? The inserts that these HTS guys.
Yeah, we're working with HTS for informal versus conventional cooling, and they provided a mold that had a bunch of different inserts. The only difference between them was the cooling channels within, so you could alter how much cooling you want the part to have, and then you can just switch out the inserts when you want to go to a different setting.
Yeah, our toolmaker gets frustrated with every time pinching him, saying, oh, "Can you fit it in that?" And then let's not worry about that straight. Put it diagonally, at least it will hold that way. And he's convincing me why it cannot be done, and so it's a very interesting debate. He beats his head on the wall, but finally we let him know this is all we got to work with, kind of. So then there's of course the point of this is. The life of the tool steel can be significantly increased by surface treatment. So a lot of the auto manufacturers, for example, when they do the stamped steel body panels and so on, right? They always go ahead and get the surface treatment of this, like nitriding, for example, is a common one, where you're not going through the entire depth of the structure, but only partially in there. But that's enough to improve the surface hardness. Chrome hardening is the other way. So there are multiple ways to enhance surface treatment. It does add to the cost of the tool, but then the life of your tool is going to be that much more enhanced. So it's an issue of economics. Will you be willing to pay that extra cost for treatment to get that many more parts? It all goes back to how many volumes of parts you're producing, right? Now, just to put this into context of automotive, as you know that every year when say Toyota or GM releases a new car of the same, same car but a new model, right? And their styling changes, their body panels, the aerodynamics changes, they may add a certain step or bend, which means they have to produce new tooling from scratch for that. And each of those tools are upwards of $1.5–2 million type of tools. So they have to have enough volume to justify that. And they always nitride those or they surface treat those in the keeping the flexibility of volume changes so that they don't have to go back and rework on the tooling as such. So tool repair also is a big business out there. There are people who just are experts in repairing tools, like creating if there's a small burr, they can add a weld to that, they can clean the weld and bring the tool back to its life. So there's a lot of art that goes into repairing of tools, or there may be an engineering change, a minor one. Sometimes you can use the same tool and accommodate that engineering change as well. So it's very interesting how that works.
But I have an example of why you would want to go with a U.S. tool maker because of that. Like I had a product line that the company I worked for was working on where they had a material change. Where it changed from like a polycarbonate with a certain amount of glass fill to a polycarbonate with less glass fill. So then the shrink and expansion changed, and they had to send the tool back. Well, the tool had been made in China,
Yeah.
and so it added like 3 months to the process.
Yeah.
And they basically had to make an entire new tool. If we'd
That's
gone
right.
with the
You
US
may pay
tool,
less
it would-
initially, but
Yeah.
then you, that's true, exactly.
Yep.
And particularly glass is very abrasive on the tool. Glass fiber is very abrasive. So even if you have like an injection molded nozzle and then the gate, glass is continuously abrading with respect to the gate, the life of that tool is going to be compromised dramatically, and you will change your part tolerances will change because simply the glass will keep rubbing against the tool and it will quickly erode the surface of the tool. The same tool will last maybe 10 times longer if you're running a knit polymer. The minute you mix glass in it, you're changing the life of that tool. So those considerations have to be taken into account. Then the final type of materials, of course, fiberglass we're talking about is glass fibers, carbon fiber tooling. So this is used a lot in the aerospace industry when you're doing like autoclave molding, for example. It's very common to build carbon fiber tools because of its low CTE for one, and carbon is very stiff, so it has the same attributes of non-deforming, if you will. And then you specially make tooling fabric. So tooling fabric has a much higher denier and weight, if you will. The 24 ounce upwards heavy toe is used for that. And when you build a tool with that, you can bulk up the thickness with just few layers as opposed to adding 40-50 layers to make a half an inch thick part. You can add maybe 10 layers and bulk it up to get what you want. But then it has the same characteristics of very stiff carbon fiber. So a lot of autoclave tools that make aircraft parts are made that way. And we have some examples as we go. So tooling selection is an animal by itself. It's not one thing that dictates. These are some things that affect tooling. Of course, like I said, part volume dictates what tool you would make. The geometry of the part is the other thing. Some materials, like it's very common in injection molding to do electrochemical etching, like or EDM machining, right? Electrical discharge machining. When you want to get very fine features in the part, you have to develop your electrodes and then cut the material to get those features in. So that is built. That's why you can build in a lot of complexity in that tool. And this does require then steel tooling for the most part. Temperature pressures have a big effect. Like he just pointed out, CTE is a big deal. If the material of the tool has high CTE, it's going to change your part quality, as I mentioned. Pressure, of course, based on is it a continuous, like a forging type of pressure, or is it intermittent pressure, or is it just vacuum? That's going to change the. And then tolerance, design intent, of course, how flexible you are, and in everything else, if you ask me what is most important, it's always the cost, right? I mean, you never can have the best of tool, but the customer should be willing to pay for it. So when you're working with tooling, again, tooling can take a life of its own in each of these material options. We're just going to assume a few today, and not with the understanding that that's not all there is to it. There's a lot more that you have to worry about. So many of you have seen these kind of tools, but I just want to make sure everybody appreciates how complex this is. So this is an example of a stamping die, right, that is used to produce the automotive body panels or other large components of that nature. Typically in this you have a very, very robust block right here, and like Stephen was saying, this kind of blocks also could be used as repeating for other parts as well. So you don't have to build the structure every time you have a new tool. You just have to produce the top insert portion of it basically. But these tools have very large stamping forces that they come about. Like if you've gone to an automotive, like a tier 1 supplier like a Camtech or Magna or CSP, that kind of companies, you'll see the parts are coming out continuous. It's progressively happening. The sheet comes, and first thing it makes a shape, then goes to the second station, makes the second shape, and this is happening in a continuous mode actually, right? So you have multiple of these in line actually. So this may be at least 200-300 feet long stations where you're going from one to the next actually. So in each thing the sheet stamps, then you see these small guys, that's the ejector that's pushing the part out, goes to the next, goes to the next. So the ejectors have to collapse back to receive the next one. So all that is very automated. So you need a lot of real estate below this tool to accommodate for all the things that are happening behind the scene, right? So that's the whole field of engineering and designing the ejection of most of these parts, because they have a lot of complexity. If you don't have something to push them out, the part will be stuck in there. And it's even more a problem with plastic parts, even more so than metals, right? So these are again body panels. You can recognize the shape of this body panel. This is making both the A and the B side. This is your B pillar that you're working on. Yep.
Quick question on the injection.
Sure.
Pins. Are those like mechanical or like pneumatic?
So all of the above, all of the above. So for very low cost work, it could be manual. You just have like a lever pushing it out. For more standard, its hydraulics is very standard. You have a travel distance of 1 to 5 millimeters sometimes. Some part may be down there, some is up here. So the ejectors are to accommodate the piano strings that you're doing different length travels like that.
You can get springs and cam actuated, gear actuated ejectors.
Mechanical system, pan, gear
Sometimes you drive
actuator.
off the multiplied node thing.
And many times plastics industry use poppets, just air actuated. Just all you do is you push a little bit of air, and that's sufficient to pull the part out. In fact, if you're doing medium volume production, that's the more preferred route, because you don't invest a lot then in the ejection. Because it can get expensive, because the more ejection you add, you have to provide more depth to the tool to hold all that ejection plate and the pins and everything. And the more taller the tool, you need a press with a higher daylight opening, and all of that adds to the cost of manufacturing. But these tools, all of them have extensive ejection built into it, obviously. But so I'll just get into a little bit of the polymer. And some of you took the class last time may recognize some of these slides, obviously. But just to recap, when we talked of injection molding, I want everybody to recall that you're feeding the powder, flakes, or pellets. Then it goes through a multi-zone here with a single screw, right? And the flights of this screw with respect to the wall will change the heat generated in the polymer, its shear rates, all its rheology, and so on. And downstream here is the contact with respect to the tool is where we are paying attention today. That's called the sprue. The sprue is where the tool actually makes connection with the feed, if you will. So the sprue then guides to, these guys are called the runners because it's running the polymer to the actual cavity. And I'm sorry, the runner in this case is this only because this is the cavity. And then there is a gate. The gate is like a gate. It opens or closes, allows polymer to enter at that location, and then it fills the part, right? And that's what, at the end, what you're happening is, in most cases, based on this setup, you can get an action where this whole thing from here on drops in the bin. So now your part has the sprue, some of the runner, and then the part itself. So then the way the tool is designed is that the gate is easy to break off, so it does not need a very high mechanical force to break that off. And that's designed so that you can say, if you buy Christmas toys, you can see that you have 20 parts all connected with everything still in place, and the child can break off each easily and then assemble something, right?
Yeah, for the high volume stuff, the medicine bottles, closures, Coke closures, yeah, a lot of those you'll see are hot runners.
Yes.
So it's designed so that there is no sprue. I mean, there's a hot sprue, but it stays molten all the time, and it
Correct.
just freezes right at the gate and comes off. Or you may, for more expensive parts, you may use a valve gate that has a physical valve that opens and closes.
And that's exactly right. In fact, I have a slide on hot runner here coming up. So like toothbrushes, I mean, you can see a lot of complex shape in all these parts, like cell
That
phone
water
case.
bottle cap.
That's right, all those are hot runners because you have a very small, like a dot there, and that's where you don't need to cut off every time. That's just, like you said, the sprue stays hot all the time, so you're not having to break it.
Yeah, I hated the sprue molds, the cold runner molds, because the sprue's always hung up.
Yep.
So you had to have somebody there to either pick it or have a robot to do
Chop
it
it
at
up,
cost to the line.
In fact, we had a job, this is actual case, we worked on eye patches, and I think I have a picture. So these are like, the patch was produced in 4, like so. So basically 1, 2, 3 and 4 parts. So this is goes on the eye, and this has a translucent characteristic, because if you look at eye surgery today, the patient either wears a white gauge or a black gauge, right? There's nothing in between. And studies have shown that if you have a translucent patch, which allows some amount of light to make its way through, the healing is actually faster. So this was the customer's need. So we produced the part, we came up with a formulation of a TPE, thermoplastic polyester, like an elastomer, but still rigid on the rigid side. It's a copolymer. And everything worked great, but every time this was the case, when you chop this thing here, this thing left a small burr, no matter how fine it was. And when you're making 50,000 of these, like he's saying, the labor you put into cleaning 50,000 patches to get rid of that outweighs all the economics you have in producing this in a fast way, right? So then we had to do a major change by going to a hot runner system so that this went away. So like if you look on the back end of your toothbrush, there's a very small dot, right? If that dot gets any bigger, and especially in contact with the skin, it's going to be very irritating for the eye. So things like that break or make a product completely, because everything worked from the function, but that was the showstopper actually. So this is where a lot of the art of tooling comes into play. Of course, Jared and probably Stephen can tell you more about this machine now, right? So, but basically, we have a machine similar to this in our facility. It's a 350-ton machine. So injection molding, when you rank them or rate them, 250 ton is not the weight of the machine. The 250 ton is, maybe this machine may weigh 10 tons at the most, right? It's really the clamping pressure that the machine can apply. And in injection molding, you have to go that high in tonnage because you are dealing with very thin parts and very complex parts. So to get the polymer into the cavity at that thinness, you have to have very high closing tonnage. So that's why this ranking is based on. So to give you an approximate feel, 250 ton can produce something of a size of a helmet, say, right, in that neighborhood. So it can make you a part about that size. If you want to make something the size of this table or a car body panel, you're talking about 1,000 ton plus machines at least. So those are huge. The footprint of this machine is about, I would say, 15 feet by 5 feet or something like that. And those machines, the industrial machines, can be very large size of this room or greater. So I won't talk about this, but there are several ways of feeding, of course, in terms of spreading the polymer inside. This is called a torpedo spreader because of the, when the polymer comes through like that, this spreader helps to distribute the flow because of the action of a diverging cone action. So the polymer is therefore not collected in a bulk, right? It is coming in form of streams up in the front out here. So ejector pins is required for pushing the polymer part out. You need a clamping force. You need generally hydraulic lines passing through the mold for heating, cooling. So there's a lot of detail that goes into tool designs for injection molding. Like I said, the attributes of this process, you're making very complex parts, near net shape. So when the injection molding part is made, usually it comes out with all these features. You have to do very little post machining on the parts. And that's where volume becomes very critical, like these kind of things. And some of you have seen this before. So here's an example of a 4-cavity tool. So when you're doing small parts, like the one I was just trying to show you, it doesn't make economical sense to do one part at a time. You build a cavity, which is multi-cavity. So in other words, you're producing the same part, 4 of them at the same time. Or at least by rule of thumb, the part sizes have to be within a certain proportion, so you can produce a family of parts at once. So if you're doing a left of something and a right of something, it could be in one mold, which is being made as a set actually. So that's quite common as well. So like I said, the sprue is what is entering, then there is the runners, there's the gate, and then this is your part. So this, as you can imagine, we're not talking in this class, but there's a lot of rheology that has to be modeled and accounted for, right? Like in terms of the flow of the polymer, it's all its thermorheological data that goes into it, whether it's crystalline, whether it's semi-crystalline. We're talking about melt flow index, molecular weight, and we saw that a narrow molecular weight helps in this case because you are breaking down the entire polymer into a flowable mass. If this was solid and half of it was liquid, you would have no control on your process and quality. So therefore that becomes very important. Yep.
It seems like the volume associated with all that infrastructure is like on the order of the part. It seems like a lot of waste.
Can't be, you typically you grind it back up and feed it back into the process.
Okay.
Yeah, these are always recycled for sure. So you're right. I mean, generally, like a Jared processes is 500,000 parts. There's a whole bunch of waste generated. But then all that can be shredded and reprocessed in the. So there's a lot of economy associated with taking the reject out of the waste.
This would not be a thermoset. This would be a thermoplastic.
These are mostly all thermoplastic, what we're talking about. Exactly. Although there are thermoset injection molded waves as well. Yes, sir.
How hard would it be? How hard would it be to get out the leftover stuff? How do you do that? Do you just pull it or?
These you mean?
No, the stride in there.
It comes with it. When you strip the shot out, usually you might have, for bigger screws, you might have pusher pins that break it free as well. But typically when you open the mold, you've got some movable action that helps pop the screw free, and then it either falls free if it's clean, or you got a picker that goes in, as we're referring to otherwise, which an arm will go in and grab the screw and pull it out. And you typically will do that so you get a faster cycle time to get out of the way, so it's less likely they hang up and get clamped on.
Also, you see this particular image here? See how the sprue's like a cone that goes near at the top? The narrow part's where it's injected, and you see the base of it, that's in the other side of the mold, so when the mold opens, it pulls that with it as well.
Yeah.
At least for this one.
Yeah, these are designed to fall off with the part actually. And where the challenge comes, like, and we have seen this happen, right? It takes a lot of time to optimize this fall, because initially when you start working, you get a lot of this stringy, angel hair-like thing hanging, which does not want to fall, and then this is going to stick, right? So that is the balance of, if you go a little high in temperature, you're going to get more of these angel hairs to fall. If you go low in temperature, you don't get the part to fill, for example. So there's a very delicate process window, and once you optimize that window, though, the parts will come in a continuous manner. So there is, and some of you have experienced it, but in some of the parts we make in industry, it's that worker who works with that machine every day who can, in 5-10 minutes, quickly get the best part right there. It's amazing just how the experience takes over in doing that.
So how much does this differ from like investment casting? Because that's the same principle for investment casting, right?
Yeah, the overall philosophy is very similar, right? In investment casting, you're producing your sprue, runner, gate system, and then you're pouring metal in that case. So yeah, there's a lot of similarities in that case. I think the main differences would be in the rheology of the systems. You your metal versus polymer, for example. It's not, I don't know, okay?
The other process challenge for these things is that you're trying to run as close to the edge as you can to minimize your cycle time. So there's a lot of work that goes into the heat transfer calculations. You're trying to balance the flow of the plastic through the sprue into the cavity so that you just fill cavities and get a good pack. And then they're already in the process, just about the process of solidification at that point, so that you can open the mold, eject the parts, and clamp to go to your next cycle. Whereas I think with the investment casting, it's probably a lot further towards the liquid end than it is towards the solid end. On the plastic, you're really trying to keep it closer to the solid end, so that a lot of the tricks that people play are how they cool the tool. There was a process, I can't remember the name, that used to allow the tool to heat up in between shots and only apply cooling as the plastic had flowed in and hit it towards the end to try to allow it to flow easier, but then cool it just enough to get it out. So there's a lot of engineering that goes into these tools.
I imagine it's size dependent, but what's the cycle time? How long does it take for the stuff to solidify enough to where?
It's very small, I mean, based on your polymer, but typical unreinforced plastics parts are in the order of 30 seconds, in that order. If the part is thicker and thinner, if it has differential thickness. But 1 minute cycle time in injection molding is a long cycle.
Yeah,
Yeah.
but like that's 30 seconds, that includes building up your shot, injecting it, holding it,
Everything, yeah.
everything. So the actual solidification after the mold is still maybe 5-10 seconds.
Very fast.
And the size, I mean, we ran tools that were 64 to 128, sometimes 256 cavities in a single shot. So you're using, a larger press, a 750-ton press, but and that's around 28 to 43 millimeter in diameter for the parts.
Right. And that's the other thing that happens is the shot size is machines are spec'd not only on tonnage but shot size as well.
So like extremely high pressure on one end and not on the other. Do you have like cavitation problems? I mean,
Yes.
yeah.
Yeah, the pressure differential is not the best of things in this because you can get very different parts. But sometimes you do use like gas assist molding, right? In gas assist injection molding, you're actually forcing the air with the polymer so that, and you can actually get the skin to form on the contact soon as the polymer hits and with the right temperature it starts forming the skin which is continuous. And then the core of this has a lot of entrapped air. So you get a differential structure which actually has a lot of lightweighting advantages and still it gives you energy absorption from the air and everything like that. So a lot of automotive bumper beams and parts with the injection molded are actually gas assist injection molded for a reason. But going to your question, Michael, is this, it's very similar except the differences are in the material and the rheology. I think we're almost close. This is going to take longer, so I may have to continue this next class, and then what I don't finish up, I'll finish it by way of a video, I guess. But I want to tell you that this system of runners and gates and sprues can get very complex as you get more number of cavities as you fill. So think of it like a tree structure, right? Like a wiffle tree, you're spreading the polymer across, and so this doesn't happen just by prayer and a hope, right? There's a lot of modeling that goes into creating the channels and what lines, what diameter they should be, where should they, what is the distance from one to the other, and so on. So I'll stop here then. I'll finally, I'm glad to get rid of these mini projects from my hand. But, I didn't lose them. I've carried it, I don't know how many cities and places.